So this is Cfrg. Hello everyone, once again. And let's start with the chair slides. I hope everyone can see them. So Alexei Melnikov, Nick Sullivan, Stanislav Mishlev, we are the chairs. This session is being recorded. We have a minute taker in CodeMD. It's Alexei Melnikov. We have a Jabber comment relay. This is Jonathan Holland. You can find the participant guide and some assistance, and you can report issues via the links that you can find on the slides. Blue shades are generated automatically based on the data tracker information, and the minutes will be able using this link. This is an OPL. I think you know this well, but if not, please follow these links. So this is Cfrg, an IETF group. You can find some information about the IETF in IRC 7418. The IETF conducts research. It's not DAS development organization. We have an agenda published at the data tracker. All the slides are uploaded, so let's start. So we have the following agenda. If some agenda bash is needed, please tell me now. No? Then let's start with the chair slides. So we have a new RFC. This is RFC 8937, randomness improvements for security protocols. We don't have any new RFCs in drafts in RFC editors queue. We have a document in ISG review. In fact, it's after IETF conflict review, but there were some minor concerns, so we hope that after the meeting, the authors can update their draft, and the argument 2 will finally go to the RFC editors queue. We don't have any new drafts in IRG review, and we have plenty of active drafts of the research group. First of all, it's SPAKE 2. It has undergone security review, thanks to Scott Flurer and Björn Hasse. There are some minor concerns about the document, so we hope that after the meeting, the document will be updated a little, and it can be moved to Shepard's review, Shepard's write-up, and then to IRG review. We have a new version of HashTKerf document. It has also undergone a security review. It was done by Thomas or Thomas Bonin. There are some small concerns about the document. I think that after the meeting, we'll discuss it with, after the IETF 109 meeting, we'll discuss it with Chris Wood and the authors and proceed with the document. We have recently obtained a security review for VRF document. Some update is needed, but all replies from the authors have been approved by the reviewer, so we think that we can go to research group last call really soon. Kangaroo 12 has gone under second research group last call. VOPRF is updated, and we'll have some update on this document today at the meeting. We have HPK document updated. Also, the research group last call is done. Now it's waiting for Shepard's review. Personally, it's me. So I hope that the week after the meeting will be enough to prepare the Shepard's review. We have BLS document updated, some news about patient-friendly curves. The document has been updated. There are a lot of concerns from research group last call, namely from Renestrik. I hope that a lot of concerns have been addressed in the draft, so it's in an active phase of work. We have Ristretto and DKF update today at the meeting. The draft has been updated also. We have a new draft AD limits that was adopted in summer. We have a status update today at the meeting. And two PAC documents that were the winners of the PAC contest, the OPEC and CPACE. For both of them, we have a status update today, and the work is in the active phase now. So information will be given in the status update slides. About three related work items. We don't have any news about C2PQ draft from Paul Hoffman. And we have two drafts in discussion. It's a draft by Philip Hallenbaker about threshold signatures in elliptic curves, and a draft from Chelsea Conlo about Frost, one of the set of schemes of threshold signatures. We have a lot of comments during adoption call, and we'll discuss this with Alexei and Nick next week, or maybe before the end of November. And some drafts are expired. Also, we have some erratas on RFCs that have been published before. I hope that we can ask Crypto Review Panel to help us with them. A brief reminder about Crypto Review Panel. Currently, Crypto Review Panel members do all reviews for all Cfrg drafts before the drafts go to research group last call. We also ask Crypto Review Panel members to help us with erratas or with documents going, for example, during PAC selection process. The members of Crypto Review Panel members on duty are on slides. Many thanks for all of them. A lot of good reviews have been made by them. Thanks a lot. So, any questions for the chairs or about the status of the drafts? No questions. Then let's go to the first status update. It's OPEC by Chris Wood. Chris, please start sharing your screen.
I'm sharing my screen. Okay.
Chris?
I'm getting no feedback. Can you hear me? Can someone just confirm whether or not you can hear me?
Yeah.
Okay, thank you. All right, I'll flip back. Just got like 13 text messages. Okay, yeah, so thanks everyone. Just going to give a sort of brief update on OPEC. Since the last meeting, we submitted the first official IETF version of the draft, and have been working with Hugo and Kevin at Facebook and getting this ready for actually shipping software down the road with test vectors and reference implementations and a lot more protocol specification clarity but there's still some more issues to be covered and resolved. So what I'll do today is talk about sort of just a high-level overview of the protocol, highlight some of the aspects that have changed since Hugo's initial version, point to some open issues that, I'm hopeful that people here will chime in and give us feedback on, and then discuss any next steps afterwards. All right, so a high-level summary of OPAKE for those who are unfamiliar with the topic and haven't read the draft. OPAKE, as it says here, is an authenticated or an asymmetric PAKE, which effectively takes a various assortment of cryptographic instructions, one of which being an OPRF, a hash function, memory hard function, such as Argon or scrypt, and an authenticated key exchange protocol, glues them all together or compiles them together into a strong APAKE. By strong, we mean that it's resistant to pre-computation attacks, wherein you have access to the salt and you can pre-compute values that might be in a password file stored on the server. So in case that's compromised, bad things don't happen. In the case of augmented or asymmetric, we mean that the client and server don't both share a copy of the same password, unlike CPACE, which is symmetric in this case. OPAKE consists of two phases or two rounds. During the first phase, clients will use their password to register a set of credentials with the server, and a set of public key credentials that are used to key the underlying authenticated key exchange protocol to actually derive a new secret. And then there's the actual online authentication flow, which runs sort of the same set of cryptographic operations as in registration, but importantly recovers the credentials that were stored during registration and then uses them to complete the authenticated key exchange. So there's this nice sort of decoupling and separation between the two, and I'll describe that visually a little bit later on. And the registration flow, effectively three messages back and forth between the client and the server. The first round trip request response between the client and the server, its purpose is to basically compute an OPRF over the client's password, so PW in this particular case. That thing is cut off. And a per user OPRF key that's stored alongside the user's password file in the password table on the server side. And then from the output of that OPRF, the client constructs what's called an envelope, which effectively just carries credentials that are necessary to complete the authenticated exchange later on. The server instructs the client in terms of what credentials need to be encrypted, what credentials need to be authenticated, and what needs to go in this envelope. And then the client just helpfully uploads that to the server, so the server can store it alongside this per user OPRF key. Very simple. The credentials are extensible, so to speak, and they are composed of a variety or a combination of what we call secret values and authenticated values. The secret values are those that are encrypted, so the server does not have access to them. Minimally, that includes the private key of the user, so SKU in this particular case. Authenticated values are those that just simply need to be authenticated in order to get the proof of security that OPAKE requires. So in this example, PKS, which is highlighted in green, is authenticated and included in the envelope. And applications are free to choose whichever sort of credential structure is important for their particular instantiation or for their particular use case. Some applications might additionally want to specify both an identity of the user, IDU, as well as an identity of the server and include that in the envelope. Or they just might want to use raw public keys as the identities of each peer. But the important bit is that the way this credential structure is constructed is flexible. The server basically tells the client what to put in it. The client obeys and happily provides the encrypted and authenticated response to the server. all of which, the secrecy of this and the authenticity of this is protected by the output of the OPRF, this F of KU with the user's password. So after you do a registration, so to speak, offline, there is then the online authentication flow. You may notice that it has a very kind of similar flow to the registration flow. Importantly, there is this OPRF evaluation, request response between the client and the server. Importantly, however, in addition to the OPRF output, so to speak, being sent back from the server to the client, the server also sends the envelope that corresponds to the particular user's identity. For obvious reasons, perhaps, and that's because the client uses the output of the OPRF and the envelope it just got from the, sorry, hold on, just muting notifications, someone texted me, uses the output of the OPRF that it just got, as well as the envelope to decrypt the credentials and derive some additional keying material, which we call an export key. I won't get into that, but it's discussed in the draft. And then run an authenticated key exchange using those credentials. But typically in an actual instantiation of opaque, you would run these two pieces together. Like you would run the authenticated key exchange in line with the actual execution invocation of opaque protocol. And you would do it in such a way that the opaque protocol messages are included in the transcript for the AKE in question. So for example, if you're running opaque with triple Diffie-Hellman, as is one of the variants described in the draft, you would simply include the credential request and response, which are effectively the messages to carry out the OPRF evaluation, as well as transfer the envelope from server to client, in the flights from the client to the server, and respectively in the flight from the server to the client. And the rest of the AKE specific bits, those particular to triple DH, sort of remain unchanged. The draft goes into details for triple DH as one of the instantiated AKEs, about how to derive keys necessary to both encrypt, parts of this particular handshake, if you were to use this, how to authenticate parts of this handshake, and importantly and ultimately how to derive like a session secret that is then used for the output of the AKE, which is the whole point of running opaque. In the draft, because we tried to describe opaque in sort of a modular way, we have this notion of configuration. A configuration fully specifies basically everything you would need to instantiate in order to implement a particular version of opaque. So as I was alluding to before, this includes minimally the OPRF, particular group, and Cipher Suite. It references, in fact, the other IRTF draft on OPRFs, a cryptographic hash function, a memory hard function, and an AKE. So two perhaps examples of this might be an OPRF instantiated with Ristretto, using SHA-512, a variant of Argon with fixed parameters or application specified parameters, and triple DH. Alternatively, another instantiation might be using one of the NIST curves with SHA-256, scrypt, and TLS 1.3 as the AKE. If you have access to the slides and you're following along, the link here actually points to a draft over in the TLS working group. Unfortunately expired, but goes into at least some initial detail in terms of how you might integrate opaque into TLS 1.3 as a variant of Sigma. And there's work being done underway to sort of resurrect and bring that back to life. So from an application perspective, there's really not much you need to do in order to make use of opaque as is currently specified. For starters, minimally, you have to actually select a configuration, which is one of these tuples previously presented. You have to choose a credential structure that makes sense for your application, although we're hoping that we can just specify some sane defaults in the draft and hopefully encourage applications to use these defaults. One of the defaults might be just simply using raw public keys as identities, and sort of punting at other kind of identifying information outside of opaque, as it's strictly unnecessary. And excuse me. Finally, there's this additional output that I was alluding to earlier of opaque called an export key. And this is really, its purpose is meant to be used, or it's meant to be used as something that is truly application specific. It's an extra key. Applications can derive more keys from it, do whatever they want with it to do more application fun business stuff. Think of it just like a normal exporter like interface to TLS or HPKey, for example. There are some use cases floating around. I'm aware of one, but I don't actually recall the details now. So perhaps someone can fill that in later. There are a number of open issues on the draft. These are some, I think, of the more important ones to complete right now. The first of which is, how much detail in terms of the actual AKEs do we need to go into this particular document? Without openly discussing the issue here, this basically asks the question, do we fully specify an AKE and its wire format in this document right here, or do we simply provide a template for other AKEs and for applications to build out AKEs like triple DH, like Sigma I, or Sigma R if they wanted to? And if we go down either path, what sort of design choices or defaults do we pick, and how many, what sort of test factors do we need to provide? And this is actually, I think, a fairly fundamental and important piece to resolve fairly quickly. So people have thoughts about which way to go on this particular issue. That would be lovely if you could share them. Another issue that's worth discussing perhaps is how parameters for memory hard functions are negotiated for a particular application use case, whether or not they're transferred in band during registration, or if they're communicated outside, it's sort of in the wrapper protocol for opaque. And then there's some other issues as well. And a link to the GitHub repository is here, and as well as on the title slide, I would encourage you to check it out, file more issues, help us improve the draft. As far as implementations are concerned, I'm aware of at least 3 that are coming up to speed. Fourth one recently that is not listed here. It's just happened over the weekend. There is a reference implementation based on a built-in Sage using the reference implementation for the OPRF code, or for the OPRF standard. There is a Rust implementation as well as a Go one underway. These are not yet interoperable, but we hope that once we nail them, perhaps some of the particulars around wire formats for the AKEs, that we can in fact produce test vectors to make sure these things actually communicate with one another. And that's basically it. So like I said, this is at least sorry, go ahead. Someone unmuted. No. Okay. Anyways, basically saying this is it's at a state where we can implement it. We have various interested people bringing up implementations, and we're working to converge on interoperability. But of course, feedback in terms of presentation, design decisions, APIs, all that sort of thing is of course welcome. So at this point, I think I just pause for any questions. I cannot hear anything. I don't know if people are talking.
Two people have joined the queue.
Who's managing the queue?
Quick question while that's being sorted out. I'm wondering if, and this is kind of a dumb question, but I'm wondering who initiates the AKE. I'm wondering if it's possible for the server to initiate the AKE and send the first message along with its response from the OPRF evaluation.
It needs the client's input from the OPRF to actually produce its response. So I'm not sure how that would work I guess, on the wire.
So it's at minimum a 2-round protocol?
A 3-round, because you need key confirmation from the client to the server. I guess Bjorn is in the queue next. Maybe you can just start talking.
Chris, one question from me. During the pack selection process, we've had a lot of security reviews, and Hugo has made a lot of efforts to provide security assessment of OPEC. And my question is whether something is needed regarding the security assessment of OPEC, maybe some security proofs or some detailed security proofs in some models, or everything is ready in this sense?
No, in fact, I think the changes that we made since the initial individual draft have made the analysis a lot easier. You may recall that one of the requirements for early versions of OPEC was a key committing AAD. However, we've sort of worked around that issue by using a one-time pad-like construction for authentication or rather encryption of envelope values. So in some sense, the design decisions we've made have simplified the lives of those who might analyze it. However, various instantiations of OPEC, like OPEC in TLS 1.3 in particular, those deviate a bit from OPEC in its purest form as written. And I think if that were to come to fruition, that would require additional analysis, either from people on the crypto review panel or the community. In particular, because the TLS integration, one of the TLS integration options is it's effectively using OPEC to authenticate the already established session secret from TLS rather than derive a new output session secret key, which is subtle, but an important difference between the two. So TLDR, I don't think the current draft requires any new analysis. Further instantiations certainly will, if that makes sense.
Okay, thanks a lot. Makes sense. Please, any other questions? 1, 2, 3. Okay, thanks a lot, Chris. Please, next slide from Bjorn Hasse. Bjorn, please share the screen. Yes, we see screen. Please start. But we don't hear you. Please turn your audio on.
Hello, do you hear me?
Yes.
Okay. So I'd like to give you an update to the CPAT draft. So in the newly formed editor team, the first step we've been doing is to make a plan on our objectives and the deliveries that we want to produce. And of course, the IRC document is one important aspect, but we also aimed at providing public code and scripts for the test vectors, and also public reference implementation for some curves, for some variants of the protocol. And we also agreed on that for the CPAT draft, we will be aiming at focusing on implementation efficiency, which means you have to decide for the draft whether you would like to have a more generic option specifying an abstract protocol, or a draft which allows for optimized solutions for several curves or exploiting specific properties of some primitives, which means, of course, some additional work. And we decided to aim at trying to find the possible optimizations in order to make implementations easier and more secure, and to make implementations more efficient as possible. And this means a little bit more work for the security analysis in order to make sure that none of the variations will have an impact on the security. So with respect to the current draft, we aim to change the text and the specification such that it no longer refers generically to groups or groups model negation, but to elliptic curves only, because this is the domain where we see the application of departure. Currently, there are two types of Diffie-Hellman protocols considered in the draft, which is firstly single coordinate Diffie-Hellman on Edwards and Montgomery curves using alligator, which have a small cofactor. And then we have a specification for X-coordinate only Diffie-Hellman on Claude Weierstrass curves, such as NIST P256. And we agreed that we should be adding a third alternative, which operates on the full group using both coordinates. For instance, if you want to use departure with ristretto. And seeing these variants, you have slight variation between the different types and different instances. Specifically regarding the properties of the hash to curve algorithm, the map to point algorithm. And we saw the need to have an explicit security analysis of all the slight variations as a first step before accurately specifying it in the RFC. For instance, if you're looking at the X25519 protocol, the secret scalars will not be sampled uniformly between 0 and the group order, but you will having a clamping function, and something which doesn't apply for the short Weierstrass curves. And we aim at consider all of these details so that existing libraries could be reused, and there's, for instance, no need for an X25519 variant that uses uniformly sampled scalars. So the security analysis is the main work item that we are working on in the editor team at the moment. As a preliminary result, I can give you information that we found an option for providing tight bounds for all the different variants. We saw that we could reduce the assumption set from the gap simultaneous Diffie-Hellman and gap computational Diffie-Hellman problems to a weaker assumption set in this step. We saw that we could reduce security for curves which have a small cofactor to the problems on the prime order subgroup. And maybe it's interesting for the hash to curve group, we found an important formal requirement for the map, which allows the reduction of the problems for the full group, which is that if you're having a point which could not be generated by the map to point algorithm, we need the property that there must be an efficient algorithm for finding an exponent such that the scalar multiplication of this point with this exponent is on the map. That's a property which is provided by all currently discussed mappings from hash to curve or used for ristretto or decaf, when on average every second exponent will do. And with this property, it's possible to reduce the hardness of the simultaneous Diffie-Hellman problem on the subset of points that could be generated by the map to the simultaneous Diffie-Hellman problem on the group or the prime order group subgroup respectively. Discussion of these aspects was not considered to be suitable for the RFC, and we are preparing a separate paper discussing all these implementation details as a first step. And that's currently the main aspect in our weekly meeting in the editor team. regarding the reference implementations, we presently have a reference implementation and test vector generation for X25519 and Alligator. It's currently still held at my private GitHub repository. There's a new GitHub Git repository under the hood of Cfrg set up, but we still need to transfer the code to this repository. And as a next step, similar reference implementation and test vector generation for short Weierstrass and Ristretto will be the next step, at least in Sage. In my opinion, it would be preferable to have also Python and ANSI C implementation so that we could check that all of these three interoperate neatly. Any suggestion regarding how to prepare this reference implementation for maybe Python and ANSI C would be welcome by us. So it would be good to have a small self-contained library which doesn't have the need for pulling in a lot of code, and of course it should be a high quality constant time code. So any suggestion would be helpful and would be welcome. So as a summary, I'd like to say that we mainly have organized our team and started the work. Unfortunately, we don't having the speed that I'd like to have, also because of the pandemic situation. It's slowing down now. The current activity is providing tight security bounds and reductions for all the tiny implementation differences that we considered. And the next important step will be to have scripts and test vectors and reference implementations for the alternative implementations. Thank you.
Thanks a lot, Bjorn. Question? And one question from me. Bjorn, maybe I have missed something, but could you tell me, are there any ideas or maybe drafts or some discussions about integration of CPACE to existing IETF protocols? We have such documents for OPEC and for SPEC 2. Do you have any process here for CPACE?
So what I've been doing is I've been in contact with others interested in providing a draft for TLS. I have a list of persons in order to proceed there, but I didn't find time to prepare a draft for TLS integration. But that would be the next step. But there's no document at the moment and no progress there.
Okay, thanks. Any comments or other questions? Please speak. Yeah. Okay, thanks a lot, Bjorn. Then we have the next presentation from Henri de Valence, Ristretto plus DCAF. Yes, please share screen.
I am hoping to share my screen.
Yes, we see screen.
And hopefully, does that slide show up?
Yes, we have. We see the slide, so please start.
Great. I see. I'm just. Sorry about that. All right. I'm gonna give an update on Ristretto 255 and DCAF 448. The draft is the name of the draft is there.
First things first, what problem are we trying to solve here?
Currently, you're not. We don't see your slides.
Oh, really?
We see your screen with
Browser window.
window. Take a window, but not the slides.
That's unfortunate. Does it make a difference if I don't full screen the slides? No, it does not.
Are you trying to figure out how to see your notes?
I can.
Yeah, maybe I can use the. No, I'm just trying to figure out how to get the.
Okay,
the
let
PDF.
let me share the slides.
Great.
It can be either. I
Right.
think you see the slide, please. So tell
Yes.
me next slide when you want.
Great.
Next.
So here we are again. Next. So the first thing is what problem are we trying to solve? Next, which is you're an implementer of a cryptographic protocol that has just come out, and you start opening up the paper that describes it. It says, let G denote a cyclic group of prime order P. And now as an implementer, you have to translate this from the abstract requirements to some concrete instantiation using probably an elliptic curve group. Next, which means that you need to choose what kind of elliptic curve to use next. And there's two common choices that people have mostly settled on: Weierstrass curve or an Edwards curve. Next, the Weierstrass curves give you prime order groups, which is what you want, whereas Edwards curves only ever give you prime order times a small cofactor. But on the other hand, they have the fastest formulas, next and next. And they have complete formulas, so they work with all inputs, and it's easy to implement them in constant time. And the kind of sad face is there because on Weierstrass curves, although complete formulas do exist, they're much slower. So, okay, we only have a small conceptual mismatch here. How bad could that be? What's wrong with a small cofactor? Well, the big problem is that the security analysis for the abstract protocol does not apply to its concrete implementation. If you want to do full validation that some point is in a prime order subgroup already, you need to do essentially a scalar multiplication, and that negates whatever speed up you would get. Or you can try to do some kind of ad hoc protocol tweaks, like, oh, for this protocol, we'll handle the cofactor by, in this part of the protocol, we'll multiply by a cofactor, and then we'll also multiply, over here, and so on. But that means that these tweaks that you do, not only do you have to analyze them, but they also cause kind of subtle quote features. So as an example of this, RFC 8032, which standardizes ED 25519, does not actually require conformant implementations to agree on whether or not a signature is valid. Next, this is ultimately downstream of different behavior between batch and single verification, and that's ultimately downstream of the cofactor. So that's pretty bad for applications involving consensus. Maybe for a protocol like TLS, it doesn't matter, but if you're doing, say, like a distributed system, that would be important. And the tweaks that you have to do, like this key clamping, cause a lot of issues whenever you try to do something beyond just the basic protocol. And this is the happy path case, right? The bad case is, next, you just have a catastrophic failure where something is totally insecure. So how do you fix this mismatch? The answer is you can use decaf and ristretto. What are these? These are construction originally by Mike Hamburg of a prime order group. Next. And what they do is they use a non-prime order curve internally to implement all of the group operations with no overhead. And then all of the work happens in this canonical, non-malleable encoding of group elements that provides you with a prime order group. And it comes batteries included with a single hash to group method that's that fully encapsulates all of the elliptic curve related math. So it's agnostic to, you know, how am I doing domain separation? Am I using SHA-2? Am I using shape, et cetera, et cetera? But all of the intricacies of the curve math are contained. Next. So how does this work? The full explanation you can find on the Ristretto Group website. So this is just kind of a conceptual overview. We're going to work with 3 families of curves. Next. There's Montgomery curves. Next, they have this formula that you might have seen before. Here I'm writing it in terms of U and V, but elsewhere you might see as X and Y. Next. These are famous because they support very fast pseudo multiplication, where if you have the V coordinate of one point, you can get the scalar multiple. And they're also convenient if you do zero knowledge proofs, because if you're in an arithmetic circuit, they require very few constraints. Next. So we have Edwards curves also. They have this formula. These are birationally equivalent to Montgomery curves. They have the fastest known formulas for curve operations. Next. And the really cool thing is that those formulas also allow parallelism within curve operations. So you can do very fun things with SIMD. That's very nice for implementations. The third is Jacobi-quartic curves, which are more exotic and not really used very much. But the reason that they're relevant here is that it's very easy to write down 4 points of order 2. And that means that you can efficiently encode a point mod this 2 torsion of order 4. And so that gets rid of a cofactor 4. But we don't use Jacobi-quartic curves. So the next thing that we do is we link up these different curves using isogenies. Curves are connected on this isogeny graph, where the curve that's in the center is a Jacobi-quartic curve for some kind of parameter choices A and D. And it's 2 isogynous to 2 different Edwards curves, as well as a Montgomery curve. And then that Montgomery curve is equivalent to a third Edwards curve. So there's a lot of different curves floating around. Next. But the idea is that we're going to use these isogenies to do the encoding. So we already got this nice encoding on the Jacobi-quartic. We specify an encoding there. And then we use isogenies to transport that encoding to different curve shapes. So we can define the encoding starting with this Jacobi-quartic, where it's very easy to write down. And then we transport that over to a curve that we might want to use for actually doing the group operations. Next. And finally, there's an extra step to handle cofactor 8 instead of cofactor 4. Next. And this kind of lets you see at a conceptual level the difference between decaf and ristretto. So using this diagram again, next. Decaf starts with a curve that was defined as an Edwards curve, ED448. And it transports from the Jacobi-quartic to that Edwards curve in the top left directly, whereas Ristretto was designed to work with curve 25519. So instead, which was originally specified as a Montgomery curve, so instead it uses the places the Edwards curve in the position in the bottom right, and it also handles cofactor 8. Next, but actually, although when we this is a conceptual picture, when we tell implementers what to do, we provide them with concrete formulas that collapse all of this into just, do these operations. It is also possible for implementations to use any curve in this graph and remain totally wire compatible with all other implementations, which is very cool. So we have 2 concrete parameterizations. One is Ristretto 255. This can be implemented using Curve 25519, either the Edwards or the Montgomery form, or you can implement it with a different isogenous curve, 128-bit security level. The security is exactly the same as the security of Curve 25519, and we've already seen a lot of adoption for zero knowledge proofs, private set intersection, PAKES, etc. Basically, any crypto protocol that you could think of that would be fun. And there's decaf 448. This uses the Edwards 448 curve, Goldilocks. Next. So you get a 224-bit security level, and you would use this basically wherever you'd use Ed 448. So for the same, basically all the same criteria for choosing between Ed 25519 and Ed 448 as a signature scheme would apply to decaf 448 versus Ristretto 255. Next. So the current status of these things, we have test vectors for all of the encoding and decoding and the various functions. And the test vectors are made so that you get coverage of all of the edge cases in the procedures, which is quite nice. We rewrote a lot of the language in the draft last year to address a first round of feedback from mailing list participants. And we've also added explicit a section on decaf 448, adding that into the spec, adding in parameters, test vectors for that. Next. And we don't think that there are any more outstanding issues with the spec. So it is, in some sense, ready to go for the next round of feedback, comments, other kinds of, the next round of the standardization process. So sorry about the screw up with the slides, but I'd be totally happy to answer any questions if anybody has them.
Please, Bjorn. Bjorn raises his hand. Bjorn, please speak. Bjorn, we can't hear you. Please turn your audio on. Yes, now we can hear you. Please tell the question. Okay. While Bjorn maybe is dealing with some issues, Henry, can I ask you to remind the chairs about the next steps, namely security review next week if no comments from the group occurs this week? Okay.
So I'm.
Please send us a reminder next week if
Okay.
No comments occur this week.
Okay, great.
Okay, sorry, do you hear me now?
Yes.
Yes.
I hear you.
Okay, so the question that I'm having is, do you plan to synchronize your hash-to-curve operation with the algorithm from the hash-to-curve draft, or do you expect that decaf and Ristretto will be having slightly different hash-to-curve algorithms in the future?
So I think ideally what we would do is have the as I mentioned, the division that is in the draft that we have now is basically at the boundary of the symmetric crypto. So I think it's totally useful for there to be a really good spec of how to properly do domain separation and everything. But in order to have compatibility with existing implementations and systems that do like slightly different choices, I think it probably makes sense to keep the same kind of, you feed, this is the place where you put in the uniform bytes, and then the curve math happens. So ideally, maybe it would be possible for the hash to curve draft to say, if you want to do hash to curve to Ristretto, you first do this symmetric operations, and then you plug that into this uniform map from the Ristretto RFC or draft or a spec.
Thank you. Please, Chris. Chris,
Yeah, I just want.
Yes,
You can hear me, right?
Yes.
Thanks, Henry. The hash to curve draft basically does what you suggest now.
Great.
In the appendix, we have basically specified 2 ways to take arbitrary input along with domain separation stuff and produce an input that you can just pipe right into basically the from uniform bytes or whatever the function name is in your document. So
Cool.
bit of respected. So I think everything is good to go from a hashing to Ristretto and decaf perspective.
Cool. So just to highlight the reason that it's that this is, I think, a really good approach is that the uniform map that's defined currently in the decaf and Ristretto spec is made so that implementations that use different internal representations can still be wire compatible on their hash to curve. So you could imagine, for instance, like a small space could use like a Montgomery form and still be compatible.
I agree, and it fits very nicely with the hash to curve graph. So I think the separation is perfect.
Thanks a lot. Any other questions? So, no questions. Thank you, Henry. Martin, share a screen. Martin Thompson, AED limits.
Right. Yes, apparently I want to share my screen. There we are.
Yes.
This should be relatively short. There's not a lot going on here. Quick status update and a couple of points on the open issues that we have. So I think Felix did most of the work here, but we've taken in the most a large amount of authentication.
We missed about 30 seconds, Martin.
Plain text and AED is going to be split, and we can provide 2 inputs to the functions that we have. That will allow people who have uses where there is more authenticated than encrypted data, they'll be able to get tighter limits in their applications. There are 2 things that I think we probably need help with, and one of the things that I was looking for here was help. I don't think that we currently have any good analysis of SIV, and there's been some discussion about what to do with adding an SIV mode section. We don't have anything there, and we don't have anything currently planned for dealing with PQ in this space. We do know that once quantum computers are around, there's going to be very different limits if we have an assumption of a quantum computer of a certain size. but we don't currently have any plans to do anything about that one. And my proposal here would be to proceed and say that the document is done, just including some caveats and notes about these things rather than having complete analysis of those in light of things like PQ. Any comments? That's all I have.
Please, comments, questions? Yes, you are. Yeah, please pick up. Yeah, please turn your audio on and speak up.
Apparently audio is on but muted.
Yeah, we can't hear you. Maybe your audio is still muted.
So I noticed that Dan asked in chat whether this would be limits for SIV generically or the specific GCM SIV mode. What's in the draft currently is very specific to specific instantiations of usage, even to the point where we have the randomized nonce, which is the I'm going to stop now.
Okay, any other questions? Then please speak up, unmute and speak up. Please push the unmute, send audio button on the top. Okay, please, Jonathan.
Who are you asking to? Who's first in the queue?
Then we hear you.
Okay. So I think you broke up in your response about SIV. So I'm wondering whether this is GCM SIV's limits or the more generic SIV mode itself.
Yeah, sorry about that, Dan. It's me to go. The draft currently has very specific limits in terms of specific instantiations of the AEADs, including things like having the nonce randomization that we use in TLS and other settings. So I would expect if we were going to do anything for SIV, it would be specifically AES GCM SIV with a particular set of bounds on all the parameters, rather than something very generic.
Okay, thank you.
Thank you, please. Jonathan? Please, before speaking, use the publish audio button.
Yeah, can you hear me now?
Yes.
Okay, so just relaying from Jabber. It says, so I just read the draft and I'm missing terms like gigabyte. It has things like P, the probability of an attack, which I don't know where people can take from. So I think it should have some kind of table with actual gigabytes you need before you need to rekey.
Is an interesting point, but unfortunately, the way that the ciphers are used, it very much depends on specifics of things like number of bytes in each message, number of messages, and a bunch of other parameters. So we can't do something as simple as this many gigabytes unless we have some bounds on that analysis. So if you look at the way that some implementations are doing that, they need to have understandings of things like typical message sizes and other constraints on the implementation, like the split between AAD and plain text. So yes, we could make a very big table with many dimensions, but that's pretty much self-service. The other thing is that we don't know what people's tolerances are for for attack probability. We don't actually have any real good guidance here on whether 2 to the minus 57, which is a number that TLS used, or 2 to the minus 40 would be acceptable. And so that's kind of something we're leaving up to people to decide on their own.
I would like to support Martin here, because really, if you add such a multidimensional table into the draft, you can always miss the issues, the minor issues that are used in the security proofs with the probabilities that depend on many factors. So in fact, such a table will dismiss some part of the information that is listed in the draft. So I would support Martin that this table is not the best idea possible, I think.
Yeah, so there's some discussion in chat there. Chris, with a little bit of help from me, put up a thing on GitHub that allows you to put a little slider back and forth and see what the limits might be under certain assumptions. So there are some tools here that just use the analysis that we have in the draft.
Mm-hmm.
It's just a little multi-dimensional.
Okay. Thank you. Any other questions? Okay, thank you. Then the next slide from Armando. Armando, please share your screen.
Hello. So you can hear me?
Yes, we see screen and we hear you. Yes. Please start.
All right. All right. So, okay, my name is Armando. I'm going to present the status of oblivious of the random function using prime order groups. So just to recall, an OPRF is the short for oblivious of the random function, as also Chris was mentioned in the talk about OPEC. This is one of the fundamental parts of OPEC. So I'm going to explain a little bit how does this protocol works. So an OPRF is a two-party one round trip protocol between a server and a client. So in this case, they want to compute collaboratively the output of a pseudo-random function. In this case, the client has some input X, and the server holds a private key. And we want that at the end of the protocol, the client learns the output of the PRF in such a way that is oblivious. That means that the client only learns the output Y, but doesn't learn anything about the K. And at the same time, we don't want that the server can learn anything about the client input or output. So we can extend that protocol and say that this is not only oblivious, but also verifiable. That means that the server now can commit to the key that is used for computing this PRF and returns a proof of that is used by the client to actually verifies whether the PRF was computed with the server key. So when we are in this verify mode, we say that we are in the case of a BOPRF. Okay, so the protocol has a setup phase where basically the client and the server agree on a cipher suite ID, and for the server, they just compute the secret key that is used for the protocol. And there are some other additional contexts, both for client and server, that are information that is used during the protocol. So in the online phase, so the client starts the communication by blinding some input that he has. We can think of this input like an array of bytes. This blind operation produces two output, which is an R and a blinded element. So this blinded element is sent to the server, which operates using this evaluate function, which actually applies this a private operation, producing this eval part of computation, and this eval is sent back to the client, which uses this unblind operation, which actually reverses in certain way the blind that was used to get this unblinded element or unblinded part, which finally is used together with the input and some additional information to produce the final output, which is the whole point of the OPRF. This whole protocol is just the OPRF. In the VOPRF, there's a during the unblind, so the client is able to verify the proof that is sent inside of the evaluation made by the server. The latest changes on the draft were including some two new cipher suite for Ristretto and decaf groups. And also we updated details about the hashing to group, because inside of the protocol, we need to do hashing to the group and hashing to scalar. And this is fully explained in the draft now. So we added that section about additive blinding. This kind of blinding allows to the client to produce faster blinding than the natural way. Also, as I mentioned, there's a complete specification of cipher parameters. There are also test vectors available, and there are a lot of editorial improvements. As I mentioned, these are the cipher suite proposed. There are two cipher suites based on one on Ristretto, one on decaf, and three cipher suites corresponding to three NEST curves and to the corresponding security levels. And also there's a range for experimental cipher suites or additional cipher suites. Finally, there are some implementations out there. So we maintain a reference implementation in this GitHub repository, which together with the draft by itself, it has some generation of test vectors using Sage and Python scripts. Some other compatible implementations are in these languages, mainly in Go. There are some implementation in Rust and also in C and C++, which is supported in Boring SSL. Well, finally, I will open for questions, and any feedback is welcome for us. Thanks so much.
Thanks a lot. Questions? Going once, going twice. Okay, thank you, Armando. And the last presentation for today is Secure Crypto Config from Kai. Kai, please share your screen.
Yes, waiting.
Yes, I can hear you, and I think in a couple of seconds we'll see your screen.
I have to select the document.
We still see only the.
So do you see?
Paste out, yes.
Okay, thank you. Hi, my name is Kai Mindermann. I'm from Germany, and I'm going to talk about the secure crypto config. So what is it in a nutshell? This is already a summary, but I will get into the details a little bit more. So it builds up on the hopefully known COSE format. And there will be a process that publishes yearly a selected list of secure algorithms, including their configuration. So not only the algorithm, but also the tag length, nonce length, and so on. And There will be software libraries that implement these cryptography algorithms and provide a simplified interface for common cryptography operations. And they use COSA as output format and use SEC configurations from above to allow both automatic and default and easier manual selection of algorithms and their parameters. So this is the summary already. Now we come to a motivation. There are certain problems with current implementations of cryptography algorithms and the APIs. So what are these problems? Mainly, it's difficult to choose the secure parameters or a combination of secure parameters. That's very difficult. Also, it's very difficult for the libraries to establish secure defaults, so to have it secure in the future. It's easy to make it one time secure, but it's a little bit more difficult to make it future-proof. And it's difficult to make the libraries misuse resistant. So everybody can use the great algorithms we just heard about before this presentation. So let me give you an example. So there are several parameters that you have to choose as developer for AES. It's what key length do you choose? Which block mode do I choose? Do I need padding algorithm? Which tag length do I choose? And which nonce length? And how do I generate the content of these parameters? And then the next question, how can I change these settings in the future? And I still can decrypt all what I encrypted before. A second example, this is about Argon 2, which is a more recent standard, which we already heard something about today as well. So there are a lot other parameters: format of the input string, length of nonce, number of threads, length of the tag, number of bytes, number of passes, and then there are even 3 different types of Argon 2. And how do I choose a secure combination or a sufficiently secure combination of these algorithms? And what is great about this standard, it already has a section which clarifies this a little bit. Yet this is still in practice very difficult for developers to choose anything of this. So in practice, usually developers rely on example code, which they find through Google, and then most often they find insecure example code, but they still are not the experts. This is what I'm going to come to here. So I'm talking about software developers' expectations versus the algorithm flexibility that we want to have with all that you develop in the Cfrg. So my assumption is that the developers are not security experts, and this secure crypto config I'm talking about is also not for the experts. There should always be the algorithm flexibility and the performance, tiny things that you can tune to make it really perfect. But I'm really talking about the average Joe, the developer that is not a security expert. And they expect, because that's what they learn and that's what we describe to them, symmetric encryption uses a key and a plain text, and that's it. But as I showed you in example 1, you need to specify a lot more parameters to really use it in practice. Also for hashing, you only expect to put in a plain text and not select various different parameters for Argon 2. Okay, and what is the secure crypto config now? And my proposal that we work on, the secure crypto config is comprised of 3 things. First, it's a process that is repeated every 2 years, at least that's my proposal, where a new set of default configurations for standardized cryptography primitives is published in a standardized machine-readable format. Then a secure crypto config interface is described that has common APIs to use cryptography primitives in software that's offered by the standard libraries. It's always easy to create a separate new library, but this will be coming outdated very soon. So it's always the best thing is to improve the standard libraries. And finally, third part is use COSA. At least that's what I found. Could be the best choice for the format, and because you can store the parameters in the output of the cryptography primitive, and then later on use this headers and keys and parameters from the output as input and derive everything from there instead of having it hard-coded in your application code and can't change the parameters anymore. And below you see the links where I worked on this already together with a student. What does the process look like? To make it a little bit more visual, we see at the top various organizations. These are just some of them. It can also be other participants. Of course, this was the earlier suggestion from me. The BSE, NIST, IETF, IRTF, Cfrg, you name it. And they come out together and agree on a certain parameter set for different classification levels. This is optional. I have a question afterwards to this, if this is a good idea or not. And then they publish this parameter set. So which algorithm, which mode, which padding is secure for what use case. And then they make that available, of course, in a machine-readable format. And then, of course, the cryptography libraries, they need to be adapted, and they must support this, because otherwise it's already not usable, and people still have to Google, how can I use AES in Java, for example. So there's something that has to be done by cryptography library developers. And this is a previous draft, as you see on the right in this description. I used previously the cryptographic message syntax, CMS, but someone at the presentation told me that COSE would be a better choice, so I changed it for the secure crypto config draft. And when these libraries are updated, then applications obviously can use these libraries in an easy way and only specify their required classification level or derive that from the document maybe they want to encrypt or hash or sign. And then they automatically use the correct algorithms from the library. And they don't have to choose all these parameters. So what are the building blocks for the secure crypto config? It's first the configuration with all these parameters I talked about. And there could of course be many per algorithm, because we have a lot of different combinations. As I talked about AES, you have different padding modes, you have block modes, you have tag lengths, you have nonce lengths, etc. And there should be one distinct configuration for each of these possible configurations with a unique name. And I think a good idea would be to use the COSE IANA registry, because they already have names for these combinations. And at least it's important that they really specify all required parameters, so developers only need to put in the key and the plain text, and that's it in case of encryption. Yes, and the output, again, it's parsable for input again, because if you want to decrypt, you need to know what algorithm was used and what's the nonce length, etc. And you need to get all this information from the output code. And this is currently not there in any known implementation. I know of, at least not in the standard implementations. There are libraries, but they will be coming quickly outdated, so I'm not considering these. And what could this look like in practice? I already worked on an interface with the student, and you see only just a quick view here. For encryption, you only need to specify the key and the plain text. And also for the decryption, you only need to specify the key and the ciphertext, and not all these algorithm modes. So this is basically just an interface for Java now, for the Java standard library. And this is what I would expect in the future to be offered by Java itself and not an interface. But it's not easy to change the standard implementation so easily. Okay, coming to a summary, what does the secure crypto config offer? It defines common use cases for cryptography operations. Then it offers a standardized configuration set for all required parameters of widely available cryptography algorithms for each common use case mentioned above. And then it establishes a process to continuously provide updated configuration sets based on existing standardization processes of the IETF. Also, the SSC allows then cryptography algorithms and now libraries to use these standardized output formats and for cryptography operations. Also, the SDC allows cryptography libraries to change their defaults because it's all put in the output formats, so they can change their defaults in the future to stay secure. Right now, there's no easy way to do that without putting everything in the output formats by default. And this would ensure backwards compatibility. Yes. There are some open questions which I want to pose here just quickly. How to proceed with standardization? Is this even a good idea to do this, to make this easier for developers? Is COSE the appropriate format to use for this? Which is the appropriate IANA registry to specify the algorithms? I think COSE is already very good. What are common cryptography use cases for developers that should be supported by the SEC? What is the appropriate security level? Or what are appropriate security levels? Because you have to select some parameters for a certain use case, I guess. And what format should be used for the cryptographic signature of the published configurations, because it should also be secure and not be changed by someone. And there are more difficult questions, but they might come afterwards. Yes, thank you for your attention. I will now switch to my browser to see you, maybe and hear you. Thanks.
Thanks. Thanks a lot, Kai. Please, questions, comments? Eric, please.
Thanks for the presentation. Oh, hang on a second. There we go. Security. I think there's some interesting ideas here, and I think you're onto something important about saying that it's hard to pick the right parameters. So I think some process for getting parameter recommendations would be valuable. I think I'm less sanguine about the idea that you're going to have machine readable and machine updatable profiles. That seems like a real recipe for interrupt failures. I see what you're saying about encoding them in the wire, but the fact is, imagine we have two COSE implementations, one of which is like just implemented in the normal way and doesn't allow secure update. It doesn't allow update, and one of which takes this thing. So now basically, the real probability is you generate parameters, which the other person can't read. Because who says the other person supports every possible AES key size, for instance? So, we spend a lot of time trying to have mandatory cipher user interrupt, and this would basically break that. So I think that so I guess I think the part about trying to specify good parameters is a good plan, but I think the part about trying to have it be machine readable and self-updating is overreach.
Okay, thank you for your feedback. Yes.
Any other comments, questions? No? Rich, please.
Yeah, hi. I'll just mention, oh, wow, let's turn off the video. That looks cool. Red Hat is doing a lot of work on standardizing crypto profiles. So it might be, don't recall if it's in Red Hat or Fedora, but it might be worth taking a look at that for a way to see, formats and what they did. And they were pushing to make all crypto using programs do that.
Can you maybe post a link in the chat?
Yeah, I can post it. Yeah, it'd be a Google search query, but I'll see what I can find.
Okay.
Bob Moskowitz just said Fedora 33 has got it in beta.
Thanks. Yeah.
Okay, thanks a lot for the comment. Any more comments on Kai's slides? Okay, thank you. Then maybe some other business. We have some discussions in the chat. I would like to comment on two questions raised in the chat. First of all, about SPAKE2 draft. There was a question from Jonathan Holland about moving on with SPAKE2 draft. The situation here is that the SPAKE2 draft predated the PEC selection process. A lot of ideas of how to implement Spec 2 inside TLS, for example, was developed before the back selection process. So after some discussions, we discussed not to stop the Spec 2 draft, and we discussed this the last meeting, in fact. There is a disclaimer in the Spec 2 draft now that the draft is not a result of back selection process. Unlike CPACE and OPEC. And so we think that it wouldn't be wise to stop Spec 2 draft, but it's the only exception, and we don't plan to do this with any PEG drafts. So we understand the question, but it was a result of a lot of discussions between the chairs. And the second question from DKG about the order of the presentations. The question was connected with the fact that VOPRF slides were after OPEC slides. And yes, I agree that since the slides for VOPRF has a lot of slides with recalling what OPRFs are, they will be useful before OPEC. But since we thought that it could be just status update slides with diffs, etc., they won't be useful before OPEC. So we decided to start with two new documents, OPEC and CPACE, which were adopted after the back selection process. But I agree that we'll try our best to address these concerns in the future. Thanks a lot for this comment. Please, any other business, any other comments, considerations for Cfrg? Maybe some comments from my co-chairs, Alexa and Nick.
Oh, it's all good here.
No comments. Thanks everybody for coming out at this time, even though we're not physically in the time zone.
Okay, then thanks everyone for coming. Have a nice day. Goodbye. Thank you.
Bye. Not what